Today's lesson, the learning objectives are moles and volume of gases at RTP and STP, understanding application of mole volume of gas interconversion in balanced chemical equation. Previously, we have learned what is mole, and we have learned the relationship of moles with the mass and the molar mass. In this setting, we will be talking about the moles and volume of the gases, how they are interrelated with each other. So there are two conventions mentioned, that we have RTP and we have STP. So let's first understand what is this STP and RTP. So STP stands for standard temperature and pressure. This is standard temperature and pressure. So when we talk about standard temperature, this is actually 298 Kelvin, and we have a pressure which is actually 1 atm pressure. So at standard temperature and pressure, 1 mole of any gas, 1 mole of any gas occupies 22.4 gm cube or liters of gas, or it occupies 22,400 cm cube or milliliters of gas. Then we have RTP. So what is RTP? RTP is room temperature and pressure. So room temperature can be any temperature, any conditions of room temperature. It could be 20 degrees C, it could be 40 degrees C, it could be 35 degrees C, any kind of room temperature. And pressure would be varied in this case in the same way as the temperature is varying. So 1 mole of any gas occupies 24 dm cube or liters of volume, or 24,000 cm cube or ml volume, which is equivalent to 1 mole of gas at RTP. If we look at these units, let me give you a little interconversions of unit. So 1 dm cube, this is equals to 1 liter, which is equals to 1000 cm cube, or is equals to 1000 ml. One can also say that 1 cm cube is equals to 1 ml. You see, there is a direct relationship between 1000 cm cube and 1000 ml. So means 1 cm cube equals to 1 ml. In the same way, 1 dm cube is equals to 1 liter. So 1 liter is equivalent to 1000 cm cube, or 1 liter is equivalent to 1000 ml. In the same way, 1 dm cube is equivalent to 1000 cm cube, or 1 dm cube is equivalent to 1000 ml. So if you need to interconvert units, you should memorize this, that if you have a dm cube, a volume in a dm cube, and they want the answer, or they want you to find out the volume in cm cube or ml, so you will be using a combination where 1 dm cube is equivalent to 1000 cm cube, or 1 dm cube is equivalent to 1000 ml. So this is how you're going to interconvert. Now let's do some real problems. For the following, calculate the number of moles of the gas. So now we are going to find out using the very same things, and we are finding out that what number of moles of gas are there. So we have carbon dioxide occupying 450 cm cube. So this cm cube tells me that this is the volume, and in another problem we have nitrogen which is occupying 2 dm cube, so this is a volume. You can use a ratio method in which 1 mole is occupying 22.4 dm cube, or you can use a formula. A formula will be shaped like this, that we have method number 1 in which we could be using a formula that number of moles, this is equals to given volume over the volume at STP or RTP. Or we can use method number 2. In this method number 2, we can take a ratio. This is actually a ratio method, and ratio method tells us that 1 mole is equivalent to 22.4 dm cube at STP, or we have 1 mole, this is equals to 24 dm cube at RTP. So we can use any method. You can use method number 1, you can use method number 2, you will end up the same answer. So let's find out for problem number 1, where carbon dioxide is occupying 450 cm cube, and we are going to find out that what number of moles are there. So this is what they are asking. Now the question comes that are they asking in RTP or STP? So let's solve it for STP. Let's solve it for STP, and let's find out that what volume do they occupy. So we have carbon dioxide, so why not to use method number 1. Number of moles of carbon dioxide, this is equals to given volume, which is 450 cm cube, divided by 22,400 cm cube per mole. So this is equals to cm cube will be cancelled out by cm cube. Now let's do some maths. We have 450 divided by 22,400. We get 0.02 moles. Now the question comes that I have given you the values in dm cube, and here I have taken cm cube. Why? Because the given volume was in cm cube, so I must convert this dm cube into cm cube. So for cm cube, we know that 1 dm cube is equivalent to 1000 cm cube. So 22.4 dm cube will be equivalent to, so we multiply it and we will get the result, and that is 22,400 cm cube. So first we look into the interconverted values, and then we are going to find out our solution. Because if otherwise I take the wrong input, just like here, like number of moles of carbon dioxide, which is equals to 450 cm cube, and I have taken the volume at STP, which was 22.4 dm cube per mole. So what will happen if we do the maths? We will get the answer, which will be 20.09 moles. So this will be a wrong answer. This will be a wrong answer. And why? Because the mole was not 20.09, it was 0.02. So you must take care of the units you are using. They should be same, they should not be different. So before solving the actual problem, why not to have same units? So first solve the same units, first get the same units, and then put it into the formula and you will get the result. So we did find the number of moles of carbon dioxide occupying certain volume using the method number 1. Now why not to solve problem number 2 using method number 2? So this will give you a clear picture of both these methods, two different problems. So now method number 2, and in this method number 2 we will be finding out that what number of moles of nitrogen are there. So 1 mole occupies 22.4 dm cube, right? So now we have 2 dm cube. So 2 dm cube will have how many moles? That is x. So x is the number of moles of nitrogen gas. So 2 dm cube times 1 mole divided by 22.4 dm cube. Dm cube cancelled out by dm cube, and 2 upon 22.4 we will get the result, which is 0.089 moles. It would be much better if you solve at your end method using the method number 1 for carbon dioxide and method number 2 for nitrogen. I think I messed up. It will be much better that if you solve at your end, that you are going to solve method number 2 for carbon dioxide and method number 1 for nitrogen. You will see that you will end up with the very same answer for nitrogen and very same answer for carbon dioxide. Now let's move on. And we have another example problem where for the following calculate the volume occupied by the gas. Now before that we had the volume and we have to find out the number of moles, and now we have the volume occupied. We have to find out that what volume would be occupied by these gases if a certain number of moles are there, because we know that 1 mole is occupying 22.4 dm cube in case of STP or 24 dm cube in case of RTP. So what if we have a different number of moles? So will they occupy the same volume or will that be a different volume? So it's a very direct relationship that if 1 mole is occupying 22.4, then definitely some other number of moles will be occupying a different volume. So let's find out. So we will be using the very same methods, either method number 1 or method number 2, whichever fits you best, you will work with that. So I'll be using 2 different problems with 2 different methods. So we have problem number 1 and we will be using method number 1. So method number 1 tells me that the number of moles of gas that is equivalent to given volume divided by volume occupied at STP, that is, why not to find out in RTP? Let's find out this problem with RTP. So 24 dm cube at RTP. So we need to find out this thing. That is a question for us. We are provided with the number of moles. We have 24 dm cube because here we have number of moles and this is known to us 24 dm cube. So we need to find out the given volume. So putting into the formula, we will get the answer that volume occupied by water vapors, this is in the gaseous state, this is equals to number of moles times 24 dm cube. This will go there and we will find out this because we are making this as a subject. So number of moles we are provided with 5.6. So 5.6 cross 24 dm cube. What do we get? 5.6 cross 24 dm cube, we get 134.4 dm cube. Now if in the next part examiner asks us to find out the volume in cm cube, then we know that 1 dm cube is equals to 1000 cm cube. So 134.4 dm cube will be equivalent to how much? That is x. So X is equals to 134.4 times 1000, and we get 134 400. So 1,34,400 cm cube is the volume that is occupied by the gas molecule of water vapors. Now for the second problem, we will be using method number 2. We have 9.5 moles of methane gas. So we are provided with the number of moles, and we have to find out that what volume will it occupy. So if we do the ratio method, like 1 mole occupies 24 dm cube. So 9.5 moles will occupy how much? That is X. So X is the number of moles, X is the volume of methane gas, which is equals to 9.5 cross 24. So what do we get? We get 228 dm cube. That is the volume in dm cube. In the same way, we can convert it into cm cube by simply multiplying it by 1000, and we get 22,800 cm cube. This is the volume occupied by the methane gas. So on your end, you can find out the volume of water vapors using method number 2, and volume of methane gas using method number 1, because for them I did solve the two different methods. So you can work them with other method to find out that you are getting the right or the same answer. So both these methods are correct. Whichever suits you best, you can use that method. Now, this was all about the first learning objective, where moles and volume of the gases at RTP and STP and their interconversion we did find out. And now let's move on to the second learning objective of this lesson, and that is the use of mole-volume relationship and balanced chemical equation. So we have a balanced chemical equation. This means that some reaction is happening, and in that reaction there is production of a gas. So we can find out, we are going to apply the stoichiometry here. We will be finding out that what number of moles of carbon dioxide would be produced here, or what number of moles of gas produced here. So we can find out that, and when we have the number of moles of the gas produced, we can find out that what volume of that gas is produced using the above relationship. So we have 6.8 grams of calcium carbonate, which is thermally decomposed to produce carbon dioxide. So this is gas actually, and calcium carbonate is a white solid. So what volume of carbon dioxide is produced at STP? So they have given us the conditions that the gas is produced under standard temperature and pressure. So let's find out that what volume of this carbon dioxide is produced. So this problem is a little cumulative problem, so let's work it out in a systematic way. So first we need to find out the scale which comes from the balanced chemical equation. So we have this calcium carbonate solid, which upon decomposition produces calcium oxide solid plus carbon dioxide. If you look at the number of atoms on each side of the equation, on the reactant side and the product side, we see that we have one calcium here, we have one carbon here, and we have 2 and 1, 3 oxygens here and 3 oxygens here. This means that the equation is all the way balanced. And this also tells us that 1 mole of calcium carbonate is producing 1 mole of calcium oxide and 1 mole of carbon dioxide. The main hero of in this equations are the one which appearing in the question. So calcium carbonate is in question and carbon dioxide is in question. So we are going to relate calcium carbonate with carbon dioxide. We are just leaving behind calcium oxide because there is nothing being asked about calcium oxide. So we have calcium carbonate and carbon dioxide. So we have 6.8 grams of calcium carbonate. The equation works in moles, it never works in grams. So we need to find out, we need to convert this grams of calcium carbonate into moles first, because our equation works in moles, the scale is in moles, so we need to have the other units into moles as well. So 6.8 into moles. For that, if we do a little recap here, we know that mass and number of moles and MR, which is M&Ms. If it is difficult to memorize, you can memorize with the name of the candy that you eat, that is M&M. So mass, number of moles, and molecular mass. So number of moles is equals to mass upon molecular mass. So first we need to find out the molecular mass of calcium carbonate. Calcium is 40 cross 1 plus carbon is 12 cross 1 plus oxygen is 16 cross 3, and the value comes out to be 100 grams per mole. This is the unit of MR. We need to find out the number of moles of calcium carbonate. This is equals to mass, given mass 6.8 grams divided by 100 grams per mole. What do we get? Grams cancelled out by grams. So 6.8 upon 100, we get 0.068 moles. So this many moles of calcium carbonates are there that we have actually decomposed, and it must have produced some carbon dioxide. Let's find out that, but what amount of carbon dioxide does it has produced? So we are going to do the ratio method using the scale. So ratio method is we have a ratio between calcium carbonate and the carbon dioxide. This is the reactant and this one is the product. That what amount of reactant is producing what amount of product, we will be finding out that. So scale tells me that 1 mole is producing 1 mole, so 0.068 will produce how much? That is X, which is equals to again 0.068 because the ratio is 1:1. So this many moles of carbon dioxide are produced. So let's find out. We have to give our answer in volume, not in moles. We need to find out that what volume was produced actually. So number of moles, this is equals to given volume upon volume at STP, that is 22.4 dm cube. We have number of moles, we know this thing, we need to find out this. So volume of carbon dioxide, this is equals to number of moles times 22.4. What do we get? 0.068 times 22.4. We get our result as in 1.52 dm cube. Or we can give our result in cm cube, so just multiply it by 1000 and you get your answer in cm cube, which is 1523.2 cm cube. So this is the answer and we have solved the cumulative problem. Now let's solve another problem in which what volume of hydrogen gas is required to react with nitrogen to produce 450 ml of ammonia gas at RTP. Now that's a bit tricky question. In the first part, we find out that we have taken some reactant and it has produced some carbon dioxide gas, which is the product, and we find out that what amount of product was obtained, and we first find out the moles because we are dealing with the balanced chemical equation, and then we find out the volume of the gas by interconverting using the mole volume concept. But here they are talking about that they want to produce 450 ml of ammonia gas. So for this amount of ammonia gas, what amount of hydrogen gas is needed? So this is a reverse problem. In here we have the reactant, the amount of reactant, and we are finding out that what amount of product will be produced. And in this we have the product, amount of product, and we are finding out that what amount of reactant is required. So let's find out that. So they want us to find out that what volume of hydrogen gas is required to react with nitrogen. This means that these two particles, these two things, they are reacting together and they are producing ammonia. So let's write down the equation. So nitrogen, when reacts with hydrogen, it produces ammonia. And if we balance it, so 2 moles and 3 moles. This tells us that 1 mole of nitrogen is reacting with 3 moles of hydrogen, and it is producing 2 moles of ammonia. So for here the question works in a reverse order. Here we are finding out that for the particular number of moles of ammonia, what number of moles of hydrogen is required to react with nitrogen. So this is in the reverse order. So let's find out that. We have 450 ml of ammonia. So the equation doesn't works in mLs or grams, they are in moles. So first we need to convert this into moles to find out that what number of moles of ammonia is produced or is required to be produced, or is the one that is needing to find out that what amount or volume of hydrogen gas is required. So we will be moving on in a reverse order. So first we need to find out the number of moles of ammonia, and for that, you see this is at RTP, so we will be using RTP. So we have 450 mLs. So ml is equals to what? Cm cube. This means that we will be using 24,000 cm cube. So given volume is 450 ml divided by, we have 24,000 ml. So what do we get? 450 divided by 24,000 ml, and we get 0.0188 moles. These are the number of moles of ammonia which are produced, and for the production of this many number of moles of ammonia, how many moles of hydrogens are required? And when we have those number of moles, we can find out the volume of hydrogen gas. So now let's do the ratio method, which is between hydrogen and ammonia. The scale which comes from the balanced chemical equation, it tells us that 3 mole when reacts with nitrogen, it produces 2 moles of ammonia. So if 0.0188 moles of ammonia are produced, then what amount of hydrogen was used or needed? So 0.0188 cross 3 upon 2, we get 0.0282 moles. These are the number of moles of hydrogens that are required to produce 450 ml of ammonia. So but they want us to give answer in volume, so number of moles. You can use ratio method here. Let's use ratio method here. We say that 1 mole occupies 24 dm cube at RTP, so 0.0282 will occupy how much? That is x. So x is equals to 0.0282 cross 24. get 0.3384 dm cube. Now, in some practices or in simple finding out the solution to this problem, we find out the result in dm cube. But if we go in a consistency, then we would see that the equation mLs were used. So we need to convert this dm cube into ml. For that, we need to multiply it by 1000. So when we do so, we will get our result as in volume of hydrogen required. That is 338.4 ml. So this is the volume of hydrogen that is required to produce 450 ml of ammonia gas at RTP. So you see that in the above problem, that was a direct problem. We have a reactant which is producing a product. In the second example problem, we have a reverse problem. Here we are provided with the amount of product, and for that amount of product, what amount of reactant is required to react together. So we did a reverse problem on the other side of the reaction. Now another example problem. What volume of each of sulfur dioxide and oxygen is required to produce 500 ml of sulfur trioxide? Now, this is not only about one of the reactant, it is about both reactants. Here we were talking about only one of the reactant, but we haven't taken care of what amount of nitrogen was required. But here you are asked about that what volume of each of sulfur dioxide and oxygen. So you will be finding about the volume of sulfur dioxide and you will be finding out the volume of oxygen needed to react together to produce 500 ml of sulfur trioxide. So a bit more complex problem. So we are moving in a progressive way. 500 ml of sulfur trioxide. First we need to convert this into number of moles of sulfur trioxide. So we have a formula here. Number of moles of sulfur trioxide, this is equals to given volume 500 ml divided by, let's work it out at STP. So we have 22,400 ml per mole. So 500 upon 22,400, we get 0.022 moles of sulfur dioxide which is being produced. So now we need to find out the scale. The scale tells us that sulfur dioxide, when reacts with oxygen, it produces sulfur trioxide. Let's balance this. So it tells us that 2 mole are reacting with 1 mole to produce 2 moles of sulfur trioxide. Now let's find out that what number of moles of sulfur dioxide is required to produce 0.022 moles of sulfur trioxide. So we are going to use the ratio method. We have sulfur dioxide ratio, sulfur trioxide. 2 moles are producing 2 moles. So 0.022 will be produced by how much of the sulfur dioxide? So X. So X is equals to 0.022 cross 2 divided by 2. You will get the very same number of moles because this is in a 1:1 relationship. So these are the number of moles of sulfur dioxide. But since we need to find out the volume of sulfur dioxide that is needed to react to produce 500 ml of sulfur trioxide, so what we do, we multiply the number of moles by the volume, that is 22,400 ml per mole. So what do we get? We get the volume of sulfur dioxide, which is equals to 0.022 cross 22,400 . we get our result, that is 492.8, which is roughly equal to 493 ml of sulfur dioxide that is needed to react to produce 500 ml of sulfur trioxide. Now let's find out for oxygen. So oxygen ratio sulfur trioxide, so 1 mole produces 2 moles, so 0.022 will produces X, so X is equals to 0.022 divided by 2, we will get the half number of moles, and that will be 0.011 moles of oxygen that are required. So volume of oxygen will be number of moles cross the volume at STP 22,400 ml per mole. We have 0.011 cross 22,400. What do we get? We get 246.4, which could be roughly equal to 246 ml. So this volume of oxygen is needed to produce 500 ml of sulfur trioxide. So you could also see that although the equation tells us that 2 parts of sulfur dioxide and 1 part of oxygen is needed, so in the mls, the values, they are different from each other. So there is a very little change in the volume that you could see that, but they are somewhere in ratios of that. But if we use a direct relationship, like if we work out the moles with 500 ml without converting it into the number of moles, we might end up with the wrong answer. So we need to work our problems in moles, and then we will interconvert it into the grams or the volume that is required. Thank you.